you know, John Gustafson recently published a book called The End of Error, in which he proposes a new floating point format called unums, which is short for universal number, and as a proposed replacement for conventional floating point. And as the book's title suggests, he makes some rather strong claims about what unums can do. So, for example, that they're easier to use than floating point, more accurate, less demanding on energy, on memory and bandwidth, or power, and guaranteed to give bitwise identical results, and in most situations faster. So, in many places throughout the book, John acknowledges the contributions of William Kahan to floating point arithmetic, of course. And so, it uses many of Kahn's examples throughout the book about how floating point can go wrong to illustrate the potential advantages of unums. So, for example, one section of Gustafson's book is entitled The Wrath of Kahn. And there's another section entitled Another Kahn Contract. So, indeed, the great debate is foreshadowed in section 18.1, where Gustafson responds at length to a challenge proposed by Professor Kahn to an early draft of the book. Now, this development has not stopped with this, and John has continued to develop these ideas. And most recently, he's proposed something called SORNs, or sets of real numbers. And I believe he will explain that new proposal here, and that will also be the subject of the debate. So the way this is going to be organized is as follows. So each speaker, starting with John, will get 30 minutes just to explain their position. And you can only ask explanatory questions, clarifying questions. Debate questions will come later. And then Professor Kahn will get his 30 minutes. And then we'll have 30 minutes of a free-for-all. But I'm the moderator. And I will make sure everybody sticks to their 30 minutes. And then we'll ask questions, and the two gentlemen can debate on it. So without further ado, it's John's turn.
All right. Thanks for this opportunity. It looks like I'm going to have to advance.
If people move closer, they'll find it easier to read the slides.
So you were gonna, okay.
So I also have a take on why this debate is occurring. It's a little bit different from what you just heard. The End of Error, UN Computing had dozens of reviewers, which included David Bailey and Horst Simon, colleagues of Dr. Kahn's at Berkeley, also Gordon Bell, John Gunnels, who has won 3 Gordon Bell Awards, and about a half a dozen other PhD numerical analysts. And the book was critiqued not just based on its mathematical content, but also on its style and its approach, since it was aimed at the, let's say, pre-college reader who did not necessarily have to know calculus in order to understand a lot about it.
Can you mic up just a little bit?
Higher?
Yeah.
How's that?
I think that's better.
Okay. Yeah, so I was purposely targeting pre-calculus people, but people who had a good high school education in mathematics. So Professor Kahn has had the manuscript since November 2013, at least a preliminary version, part 1. And we had email conversations about it, but all email cut off, strangely, in July 2014. We've been going back and forth. And I posed a counter question to him. I said, can you solve this one? And then the line went dead. I didn't know what I'd said, but it's possible that health problems were involved. But I was really missing his contribution because I wanted to make sure he was on top of everything I was about to publish and would be able to give me his feedback. Then this happened. The book came out in February, and fairly quickly became the #1 bestseller in numerical systems. Admittedly a small category, but there's 4,000 books numerical systems on Amazon, and he got 8 reviews of 5 out of 5 stars, and they kept running out of the thing. They couldn't keep it in stock. And I think this is probably what roused the attention of Dr. Kahn, is because people are actually reading this thing. Maybe we should do something to caution people about it. So, The Wrath of Kahn, a bitter blog. As you may know, Dr. Kahn no longer really submits papers to journals, at least not very often. What he does instead is he writes blog articles, and some of them are very colorful, let's say. You know, like how Java's floating point hurts everyone everywhere, and things like that. And he prepares these diatribes and he blogs them and usually labels them as work in progress. I don't know if that means he changes them occasionally or not. But the issue we're discussing today, the future of number representation on computers, I think is too important to be left to the bickering of 2 old men. So, he was kind enough to share with me 38-page attack he wants to post about the end of error, arithmetic. And so I was able to see some of the things he plans to say. I expect him probably to be covering some of these things today. Since this is the only thing that's really finished, I'm only going to be talking about what are now called Unums Type 1 or Unums 1.0. I don't have any material prepared about 2.0 because, in fact, I'm not finished with it yet, ready to show the world. It's still in progress. So I will respond in part here to the bitter blog that I have seen. You see the table of contents there. I'm sure you can't read those words. First of all, I think everybody has this reaction. Variable bit size is just too darn expensive. Be able to change the widths and sizes of representations is going to be a headache for hardware designers and for software and for storage and so on. And I always sigh and say, well, it doesn't have to be variable size. You can do these things fixed size. But if you do have to use variable size, you don't need an additional set of pointers in order to pack and unpack these things. There's these three fields, the U tag. They serve as a pointer to the next unum. So you untangle it as a linked list. They already have the overhead necessary for packing and unpacking. No additional bits required. So, chapter 7, the title of the chapter is Fixed Size Unum Storage. And I don't know how people can miss it. It's 93 pages, 93 to 102, talks about how you can make sure that you can fill matrix arrays with unums and still be able to have constant time access to anything and do exactly what you would do with current arithmetic. No problems. There is still energy and power savings when you unpack things, leaving a few bits unused. Hardware designers know how to turn off bits with the absolute certain fields within, say, a 64-bit register are not going to be touched. So even within the chip, you can still get energy, power savings in unpacked form. Now, this brings up an example that Kahan calls a bogus analogy. Here's what I put, the version of it. In Courier, 16-point type, unums offer the same trade-off versus floats as variable width versus fixed width typefaces, harder for the design engineer and more logic for the computer, but superior for everyone else in terms of usability, compactness, and overall cost. Do that in times and notice how much space it takes up on the screen, or how much space it would take up if printed. Everybody I know who has read this understood the analogy, except Professor Kahan. He said, bunkum! Gustafson is confused the way text is printed or displayed. It would occupy more DRAM memory, not less. Yeah, it takes more DRAM memory to take less space on a piece of paper or on a screen, which might be the most valuable resource these days. So I was saying that if you have more memory, you can do certainly tighter fitting of things, but they only have to take up the amount of space that they each require. Instead of everything has to be as big as the largest letter. So the same way, if you have variable size arithmetic, you can shrink and adjust, and in general you will save space using only as many bits as are needed in memory for the numbers. So I have not met any other reader who misunderstood this and then attacked it. But here's the fallacy, and it's a willful misunderstanding technique. You take something I've written, or anybody's written, and misread it to be something that's clearly a false statement. Then you attack that, even that's not what I said. So as I read through this 38-page document, imagine 38 pages of text just like this one. I didn't say that. So he's attacking things that were not the position I was taking at all. I want to go over a classic Kahan example. The area of the triangle that's very, very skinny. So let's take a triangle size A, B, and C, where C is the long side, and A and B are just barely more than half the length of C. So it pops up a little bit like buckled concrete in the sun. And it's only 3 ops larger. And then you're going to try to use the formula, the classic geometric formula of square root of S minus A, S minus B, S minus C, after finding the sum A plus B plus C over 2. And this is hazardous because of that. S and C are very close. In fact, they're only 6 ops apart. So you're going to be taking 2 very similar numbers and subtracting them. Not necessarily a problem if it's exact. You don't lose any information if those 2 are properly represented. But if there's any problem that you rounded S when you calculated it, that's going to amplify the relative error in a massive way. So in IEEE quad precision, let's pull out all the stops and use the best stuff you can get right now. 128 bits, 34 decimals. We'll let A equals B equals 7 halves and add 3 ops. An op is 2 to the negative 11th, 111th power. That's a really small number. And C equals exactly 7. And just to make it a little bit more interesting, let's say that the units of length are light years. So 7 light years away, that's like Alpha Centauri in each direction, our nearest star. 3 ops is 1/200th the diameter of a proton. Amazingly, that manages to pop the triangle up by roughly the width of a standard door, 85 centimeters. So finally, we have a number we can kind of comprehend. And that area of that extremely long strip is about 55 times the area of the Earth. It's getting almost up to the surface area of one of the gas giants like Neptune. So here is the answer correct to 34 decimals in square light years. Just remember the first few decimals, please. It's easy to remember 3.14 times 10 to the minus 16th square light years. That's what we should get. The quad precision float result is it gets 1 digit right. A lot of work for 1 digit. 3.6 times 10 to the minus 16th. About 15% too high. That's, in terms of ops, that's 250 some peta ops. The result does not admit any error nor bound it. It gives no warning to the user. You are expected to do error analysis in order to figure out that this happened to you because it's completely silent. Nothing protects you from this error. Professor Kahan suggests that you sort the sides so that they're A greater than B greater than C, and then apply this formula, which is algebraically equivalent. I would love to know how many hours it took him to find that formula, or how many hours it would take you to figure out that formula. Half an hour, okay, half an hour of a Berkeley professor's time. Conservatively, let's suppose your time is worth $300 an hour. I think it's probably more. So it cost about $150 to get that formula out in order to save the computer from having to do a little bit more work. That's now provably within 11 ops of the correct area, but it takes hours to figure out that kind of an approach. It also uses twice as many operations. I have no objection to using twice as many operations. We've got operations to burn. But that's not the issue. It's the people cost of the approach. It's the wrong direction. We need to make things easier for users. Let's try Unum arithmetic, and let's make sure that we're not cheating. So I'm not going to use any more than 128 bits, period. We're limited on the quads, 128 bits per number, but it can adjust. It will sometimes use less than 128, but it will never go over. The exponent is more flexible. It can go from 1 to 16 bits, so I've actually got a bigger dynamic range. The fraction can be 1 to 120 bits plus the hidden bit. That's higher precision than quad. The result is a rigorous bound accurate to 31 decimals. The area is strictly bounded by those two numbers. They don't start even differing. You see the orange over there until the 32nd decimal. And I didn't have to change the formula. The area of that bound, the error, is a square about 8 nanometers on its side. So we're getting down to about the limits of present lithography in order to find out the error in binding this thing that has 55 times the area of planet Earth. Okay, so in summary, let's take a look at quad precision IEEE floats versus Unums, also 128 bits. The dynamic range is almost the square of what you get with quad precision floats. Instead of 34 decibels, I could have up to 38.8. And then trying it on the triangle, I used an average of 90 bits. They shrink. And the result is, the float result says area exactly equals this wrong number, versus Unums which say it's definitely between these two numbers, provably. The type of information loss in the case of the float is invisible error. Very hard to debug. When I actually did this example, I used Unums to do the quad. I just set the exponent to the right size and the fraction to the right size and simulated it with my environment. And the point where you get the rounding error, where suddenly 6 ops becomes 8 ops, is instantly visible. It was so easy to spot. There was no problem. Whereas I think if it just keeps on cranking away, always giving what looks like 34 decibels of precision, you're going to have to walk through it one step at a time, very laboriously. So by having more information, it makes it easier to debug and figure out what's going on in your computation. Here's another example of, well, just rewrite the code this way. Now I did an example just to show why round to nearest might not be random, and also how the system could automatically adjust to give you higher accuracy and manage self-managed accuracy. Simplest example I could think of was just count to 1 billion. Just keep on adding one, adding one, adding one 1 billion times and see how you do with floating point arithmetic. Floating point floats, of course, can represent the number 1 billion, but they will get stuck, as we heard in an earlier talk. In trying to count to 1 billion, IEEE floats get stuck at 2 to the 24th, 16 million something. They can't get any higher because if you add one, it keeps on rounding down. Well, this is a well-known problem, and Dr. Kahan says in his write-up, compensated summation will be illustrated by application to a silly sum Gustafson uses on page 120 to justify what unums do, as intervals do, namely convey numerical uncertainty via their widths. I don't think that's silly at all. I like to know when something has suddenly lost its ability to give me a precise answer. And that's actually not what this section was about. But let's try it. So, this is a screenshot from Kahn's paper with n equals 10 to the 9th, compensated summation, all in floats, except the sum. Now you introduce two new variables, old sum and compensation, and you keep track of this. Your summation in a program often will be scattered all over the program. So for every sum you're accumulating, you're going to have to keep two auxiliary variables like this and keep track of them. What do you suppose this does for the maintainability of the code and the portability and the chance that you might have made a bug somewhere, made an error? I'd say it goes sky high. So I coded it up in Mathematica exactly as you see here. It's a slight translation from whatever pigeon language that is to Mathematica, but I think it's exactly what you see. And I summed from 1 to 10. I got the number 2036. I tried adding 1 plus 1. It gave me 4. I tried going all the way to 1 billion. Nan. I think sum minus old sum equals infinity minus infinity. It said not a number. What is going on? This is a fail. He got an error when he coded it up. And he put it right there in the code, in the text. So even Kahan didn't get it right. Rewriting code to try to compensate for these things and say, let's rearrange all this stuff, is very error prone. It also makes your code completely cryptic to anybody who's trying to understand. What are you doing? You just won't be able to see it. Plus, it gets potentially huge mistakes. So an approach that uses more coding effort and 3 times as many bits to produce a wildly wrong answer does not impress me. Examples like this need to be tested, not merely asserted. He says sum equals 10 to the 9th exactly. No, it's not. I wonder how many other things he says this is true for this formula. When I wrote the book, I did not use a word processor. I used Mathematica to generate the book as a computer program. All of the examples, therefore, are computed output. So any mistake it would make would be like transcribing a result somewhere into the comment field. I might make a mistake doing that, but other than that, it's all pretty much bomb-proof. Now I had one of my favorite examples from Dr. Kahan is, I called it his monster, and that's meant as a flattering term, because I think it's a really clever example. But it's a very tough one for floats. There's 3 functions, t, q, and g. I got the letters right this time, I think. And q should be identically 0, but floats can't do the square roots and the reciprocals exactly, so they tend to get a little slop. You square that number in the bottom function, g, and that means you're going to get something a little bit bigger than 0. And then you use the removable singularity function, e to the z minus 1 all over z. And floats will tend to get 0 most of the time. They might get lucky and actually get 1, which is the correct answer. Okay, so when I coded this up, I used the approximately equal sign, which actually means intersects. So if a unum interval intersects 0, then that's the wobbly, not nowhere equal sign. I didn't use exact equality there, shown in bright blue. Just the way he showed it in bright blue, because he wanted to emphasize that I was cheating. So he got bent out of shape by that. So I coded it up with an equal sign. And you can see right there, if z equals 0, 1, else e to the z minus 1 over z. I don't know how much more direct I could code exactly what he wanted as his example problem. The other 3 lines are just putting it in unum form with unum operations. Here's the result. Instead of getting exactly 1, I got 1 plus an O. I showed you the first 9 and the last 9, but it's very boring. A list of 10,000 numbers is all exactly 1 and an O. And they're all the form 1 plus epsilon and it's rounded on, this is a half open interval. It includes number 1, and it's a little bit bigger, goes a little bit to the right, but it's never 0. Never makes that mistake. Now, he would have found that out if he'd tried it. He has access to all my code at his fingertips, as do all of you. It's a free download. Comes with, just go to the CRC publication site and use it. Or you can get it in Julia, or there's about 5 versions of the Unum arithmetic now in Julia on the web. One in Python, that's a line-by-line transcription of the prototype. So, C versions are popping up everywhere, C++. It won't be long before, name your language, it's going to have some Unum support from somebody. So I don't know why he didn't just try these things and he said, oh, that's not going to work. He speculated that it would fail. So he made one up, and I feel so honored. I earned my first targeted, this will break Unums from Dr. Kahan. What he did was he added on a number 10 to the negative 300th power, all raised to the power of 10,000 times x plus 1, which could be as large, I should say as small, as 10 to the negative 30 billion. So I'm very flattered that he thought it would take a number like 10 to the negative 30 billion to break Unum arithmetic, or at least slow it down, make it take an intractable amount of time. What, if anything, does Unum computing get for this? How long does it take? It cannot be soon nor simply 1.0. I bet. Had absolutely no trouble handling this, and it didn't slow it down one bit. For a very simple reason. What he called that very small number is immediately turned into the Unum 0 to epsilon, open interval. It's not 0. It's too small to represent. This is the way Unums handle what normally would become underflow. They don't underflow. They don't overflow, and they don't round. They just say it's in that interval, 0 to epsilon, and I will keep track of it that way. You want to exponentiate it? Fine. You'll get it, once again, 1 to 1 plus epsilon. It didn't go any slower. It didn't require high precision. I guess you could say it just gave up. It didn't even attempt to represent this number. And Dr. Kahan referred to it as an infinitesimal, which I think is a strange use of the word infinitesimal, since it's clearly a number, not an infinitesimal. Anyway, here's what I call an inconvenient infinity. And I just was finding a very simple example. As I say, this is a very broad audience book. So I said, what's the area of a circle? Let's give it an arc of a circle, multiply by 4, and see how close to pi we can get with 1 decimal of precision, with very, very crude limits. So if you divide, if you pick a point on the left, it will kind of like a burning fuse, move over to the right and close the gap of what evaluates to x squared plus y squared equals 1. All you have to know is how to multiply and how to test for equality with 1. The error tends to be 1 over n, and it's a rigorous bound. This works on any continuous function. It doesn't care. In fact, with slight modification, you can even work on discontinuous functions. So I was looking for generality, not for how tight can I make the bound. So here is one of the things that Kahan wrote up in his attack on my book. He mentioned that the midpoint rule has an error term associated with it. The trapezoidal rule has an error associated with it. And if you use those two together, you can put a, quote, bound about numerical evaluation of intervals. Pretty good. It does require that the second derivative exist and be bounded throughout. And as I read through his write-up, he mentioned several times f prime is bounded throughout. And then he sort of noticed that it's not. It's not bounded. For the quarter circle, it goes to infinity. To my astonishment, he used the formula anyway. He used the bound, ignoring the fact that this bound plus infinity is less than. You can't do that. If my students do something like this, I take off at least half points on the test. Okay. There were very clear conditions for this theorem to work. And he ignored them because he wanted a nice tight bound. He also said that my method is order n squared, which I think if you just look at the method, you can see it's not order n squared. I do give an earlier method in which it populates all the squares underneath and quickly say that's not the right way to do it. You do it this way. But he's still stuck with, oh, that's a really slow way. It would be very, very slow to just fill in all the squares. There's too many mistakes to really cover here, but perhaps the biggest one is he says the book claims it ends all error. It does nothing of the kind. It says it ends a specific kind of error. It's the error of rounding and sampling. Always substituting a specific exact number when you really wanted something different. And he says unums are target intervals. Well, unums subsume floats and intervals. You can use them to be floating point numbers. You can use them to be interval numbers. This is a whole environment. It's not just a number format. It's a set of rules for how to use them as well. What you can do in Scratchpad, for example. That's what gives you bitwise compatible answers. But, you know, targeted means like too much lipstick and makeup, things like that. And when I look at these 34-digit numbers that claim to have all this precision, and only one of them is correct, I think that's the one that's wearing too much makeup. You see, unums admit what they don't know, whereas floats always claim all this precision, which might not be true. Gustafson regards calculus as evil. He is not joking. I was amazed because I used a raccoon meme that says DIY LOL on it. And I don't know how anyone could know that I'm not joking. I have invented something evil. I will call it calculus. I think most people would laugh when they see this, and that was my intent. I was trying to make a point that people tend to confuse when they're calculating and when they're using calculus. We get in a lot of trouble doing that, and there's a lot of problems that can be solved without using calculus. I wanted to kind of push the limits. How far can we go without requiring calculus? Anyway, I would say in a few places that grade school math would suffice. And you say, that's not grade school, that's trigonometry. And, well, 12th grade is a grade. 11th grade is a grade. That's why they're called grades. If I meant elementary school, I would have said elementary school. This is not a book for elementary school math. Unums will cost thousands of extra transistors. Really? Which will cost thousandths of a penny? This is 2016. This is not 1985. 1,000 transistor will cost you roughly 1/100th of a cent right now, and it's getting cheaper still. His approach is very inefficient. Here's a faster one that usually works. How many times have I heard that? I am so tired of methods that usually work and require an expert to tell you when they do work and when they don't work. I'm interested in very robust methods that you can hand to people who are not experts that work every time, even if it's slowly. Gustafson suffers from a misconception about floating point shared by von Neumann. It pleases me no end to share misconceptions with John von Neumann. One of the ones, the misconception he was talking about actually is von Neumann was concerned that if you handed floating point hardware to people, they would misuse it. They would just use it blindly without doing proper error analysis, and they would get in trouble because they'd get wrong answers and they wouldn't know it. That's my misconception. I think it's perfectly accurate. Let me just give you some memes. That was computers then, 1980s. Remember those days? This is computers now. 1,000 times cheaper, 1,000 times faster. Here's what arithmetic looked like back then. Single, double, extended. Here's what arithmetic looks like now. You see my point? Isn't it time to do something about floating point arithmetic? Maybe not what I did, but something to improve the quality with 1,000,000 times as much power at our fingertips? Why can't we do something to make things a little less painful for people? The biggest blind spot of all in the entire 38 pages of criticism he's levied, and watch for this when he speaks, because I hope he doesn't make it now. I say several times, remember, there is nothing floats can do that unums cannot. They are perfectly capable of mimicking every float that there is, all the IEEE floats and all the sizes in between. That's just special cases of IEEE floats. It's the last line because I want to make sure people saw that. There's a whole chapter dedicated to this called Permission to Guess. Because what you do with unums is you explicitly ask for a round operation. It doesn't happen every time. So you don't have to throw away all these great float algorithms that we've built up over the decades. I'm not saying you should. There are many things, well, there's quite a few things you can find where a floating point algorithm is perfectly stable. It works, it's got a solid base of theory behind it, and there's absolutely no reason to use unums. In fact, unums may complicate things to the point where you really wish you didn't use them. Then just use the unum as a float. It's a superset. When you request rounding, it's very much more honest than when it happens every time without you being under control. Unums end the era of mandatory, invisible substitution of incorrect exact answers for correct answers. It gives you back the control over what's going on in the calculation and makes it so visible that you have a much better chance of knowing what went wrong if something goes wrong with your calculation. It's easier to debug, far easier. Float methods are especially a good way to deal with the curse of high dimensions. If you aren't careful, you do get a kind of a 2 to the nth effect when you're trying to solve something that has n degrees of freedom. Whereas maybe there's a float method like Gaussian elimination that solves the equations with order n cubed. You can use that to get a first guess, and if you want to do more with it using unums, you have that option. If not, you've got way more flexibility in the precision and the dynamic range than you've ever had with IEEE floats.
Sorry, do you mean float or unum methods?
Did I say something wrong? Float methods, using, in other words, take a method that exists as a float method, use the unums to do the float method, use that algorithm, use that numerical method. Like Gaussian elimination does not work well with intervals. Bad idea. Okay, it just explodes. You get a huge bomb, and it's not useful. But I did mean float methods here. So use unums to perform float numerical methods. You can do them. So as I look through these pages, I see things that you normally wouldn't find in a math review. And I know invective worked for Donald Trump, but is this really the right way to discuss mathematics? I mean, every time somebody proposes, seriously, let's do something about floating point, there's this thing that in my head, I envision it kind of this way. The Lord of the Reals does not share power. Something lights up over Berkeley, and pretty soon, the blogs are just darting out and saying, that's wrong, and that will never work. So I'll leave you with that, and Dr. Kahan, it's all yours.
Well, while you were out getting my slides up, what John has done here is to take examples out of context, starting with the triangle. The flat triangle was not the issue. The idea was to show that floating point will get results that are excessively wrong compared with the condition of the problem. And so if he had chosen a somewhat different triangle, then we could have asked the question, well, how does your answer's error vary with the uncertainty in the data? Suppose the data is uncertain by a unit in the last place. Well, it turns out that for that flat triangle, the uncertainty is about right. For a different triangle, you get the same horrible uncertainty from Heron's rule, but it's not deserved. In other words, you can't tell with ordinary floating point arithmetic, unless you do an error analysis, whether what you're getting is deserved or not. And what John is saying, in effect, is you don't have to do an error analysis. You just have to use unums. Well, I'll answer the other issues that John raised on our time, but my time I'm going to use for something else. Let's observe. You can read this at your leisure because it's posted.
So you need to, are you wearing the microphone?
Say again?
You need to use the microphone.
Do I need the microphone?
Yes.
Yes.
Okay.
I do, but all I should turn is.
It's okay. I'll use this one. It's not a problem. If I can just get it turned on. Now, is it working now?
Hold it up.
Do I have to hold it here?
Yeah, that's good.
Okay, that's fine. Let's observe. You can read this at your leisure because it's posted on my webpage. And if we go to the next page, please. The detailed critiques are here, so you can see whether John has represented or misrepresented the criticisms that I levied. You can read it for yourself. But these are the documents that we exchanged. Those are John's documents. And then I exchanged the first drafts of these documents. Let's go on to the next page now. Here's the issue. It takes a long time to correct a mistake. And in any event, the arithmetic is a small part of the issues that we have to face. Let's go on to the next page, please. First of all, what are unums? Well, I said they're counted intervals, and so they are. Floating point numbers, each has its own width, range, and precision. You can vary it as much as you like. Each is tagged to show if it's uncertain or not. Usually you'll use them in pairs because they're endpoints of intervals, although they may not be included in the interval. And they're alleged to save storage space. Ah, that's going to be the critical issue. Do they really save storage space? And ideally the widths would vary automatically. Of course, that would happen with interval arithmetic if we could get it with varying precision. But the people who are trying to standardize on interval arithmetic have enough trouble grandfathering in little schemes, so they aren't interested in that. What about sorns? Sorns don't have variable precision. You've got to commit yourself. They're finite collections of extended real numbers. That means that they include infinity. They allow open intervals. They also serve in pairs. And they too will save storage space because what you manipulate are not the numbers, but pointers to the values. And so it's possible to run this arithmetic very, very fast. Now both schemes are intended for use with massive parallelism. And when we look at this, we'll see how massive the parallelism may have to be. Next, please. The issue here is not so much whether they would be worthwhile if what John says were true. They would be. It'd be lovely to be able to get away from error analysis. I would rather do something interesting. But you can't. And it's possible to prove it from fundamentals. However, rather than bore you with fundamentals, I'll try to give you counterexamples. Let's go to the next page. What are the extravagant claims? Well, he says you don't have to understand any difficult mathematical analysis. In particular, the discretization of the continuum when you're solving differential equations. You don't really have to understand what's involved there. You don't have to worry about underestimating the uncertainty in your data, and you don't have to worry about round-off. Well, that's interesting, but it isn't true. None of that is true. Sorn computations, they have a different system. And units and sorns are not independent of the dependency problem of interval arithmetic, nor the wrapping effect, although John does claim they are. He claims, oh, the error grows only linearly, but that's not quite true, as you'll see. He claims that calculus is evil. Okay, so he's got a funny cartoon, but he really does disparage it. He says you don't have to know it to solve differential equations. He says you don't have to know modern numerical analysis nor difficult error analysis. That's what he says in his book. You can read it for yourself. And then we've got a problem here with diagnostics. A plethora of nams, he says. We've got too many nams. He doesn't know what they're for, I guess. And flags, inaccessible for most programming languages, so they just annoy people. Although if they're inaccessible and you can't use them, why would he be annoyed? Well, there's nothing slow about them. Directed roundings, well, you don't have to worry about those because unums and sorns don't have directed roundings. There's the trouble. And that's what we have to combat. Let's look at the next page. Can we be liberated from error analysis? Well, in order to understand the issues, we have to look at the process. First, you choose an algorithm. You express it in a mathematical language, and you prove that it would work if you did it in ideal arithmetic with infinite precision. Then you translate it faithfully into a program in some programming language. Then you execute the program, and you get a result. Now, these three things are different. The result might not be accurate enough. You have to cope with that. I mean, usually it is, but often it isn't. So there's this question. If P's arithmetic is floating point, whatever the precision, do we have an error analysis to determine for sure if the program P implements the algorithm accurately enough? And the answer is maybe you do, and maybe you don't. And if you do, it may cost you a fortune. First, to find it, you have to pay some PhD guy for quite a while to look for it. And then if he finds it, it might cost you a fortune to compute that error bound. So that's why people are unhappy about floating point arithmetic. And if unum arithmetic did away with that, wouldn't that be lovely? But it doesn't. Next page, please. We're going to be disappointed. We're going to be disappointed because when we affect the discrimination among the function we want to compute, straight f, and the algorithm we hope to compute it, could be a formula, curly f, and then we have big F, which is the program, they're all different. When you execute this program at an ordinary floating point, it could be arbitrarily wrong sometime, for all we know, without an error analysis. And of course, what we'd like to do is something about that. And what John has in mind is to use unums, but there are other ways to deal with this problem, which I'll get to later. In fact, they were even mentioned at this conference yesterday. Now, what about Zorn or Unum interval arithmetic? Well, the trouble there is that f can be an interval that, although it encloses the ideal mathematical value, can be awfully big. And if it is terribly big, too often, then you won't do it. If the big width is due to round off, there's something you can do about it. You redo the computation with appropriately higher precision. Of course, that means you have to have interval arithmetic with variable precision. Well, good luck finding that. Unum computation lets the precision be increased by the program, and often it works. If the big width is due to uncertain data, now you have a different problem. And what you have to do is break up the data into small subregions and replace f evaluated once over the block of data by the union of all the intervals f with little x in here. And often the union is smaller. That often works. The trouble is, they don't always work. That's the issue. If they always worked, we would celebrate, but they don't. Next, please. So here are a couple of failure modes. How can increasing the precision of unums fail to overcome round-off? Well, it can, and there are examples. The trouble is that they're so subtle that I'll explain them only in the question period. It takes too much time now. What about this union issue? How can the union of f of small intervals fail to be smaller than the overside f? Well, here's a simple example. This is a rational function which has two expressions. This expression and that expression are the same rational functions in the field of rational functions. Well, why would you use this one? It's more accurate when x and y have approximately equal magnitudes. Why would you use that one? It's a better choice when x and y are such that over-underflow might threaten you, so you might use one here and another one there in your program. Let's look at the open square. It turns out that both in Zorn and Unum arithmetic, you can represent open intervals. So this square is representable. And now, if you subdivide it into little bits, no matter how tiny they are, you'll always find that the union of the regions with little bits is always this interval. Whereas the correct one is that, except for a misprint. Those should be round parentheses. It should be an open interval, not closed. That's what this thing reminds me of. So, the trouble is that if you don't use the right expression, you may end up with terribly wide intervals. And that can happen to unums, and to intervals, and to Zorns. Next, please. Well, how often does something this bad happen? Well, it's an instance of the dependency problem. The interval arithmetic people know about this. The books, chapters claim that they've overcome this problem. And the documents about Zorns claim you have no dependency problem. Those are their pages. Well, it turns out that that isn't quite true. Now remember, you want straight f. That's what you want to compute. But you're going to use an algorithm curly f. And you're going to write a program called big F. And the trouble is that big F may be perfectly happy with floating point numbers. It just misbehaves when you use intervals. That's what happened to our on the previous page. I don't know how you'd ever figure this out if you didn't have an alternative way of doing the computation. But there's another failure mode. You see, it's possible that the algorithm you chose, although it would, in infinite precision, compute the right function straight up, the algorithm you chose may be a really bad way to compute what you want if you have rounding errors. And that may be true no matter how this is programmed, interval arithmetic notwithstanding. And there's an example. The incenter of a tetrahedron is the center of the biggest sphere that fits in the tetrahedron. And no matter how you program the function, units, intervals, whatever you like, as the volume of the tetrahedron shrinks, the value you compute goes off to infinity. And this example is in some of my notes, and it's also in one of the pages, one of the documents that I told you about. Another way of things going wrong is that curly f may be the solution of an equation. Now, this equation might be satisfied by the ideal function, that's what you want. And what you've you've got is an equation manufactured for curly f. That's your algorithm. Solve this equation. The trouble is that the coefficients can depend on your data. And if your data is a little bit uncertain, then the coefficients will be uncertain, but they're correlated. And they're correlated in a way that all interval arithmetic schemes ignore. So that means the equation solution may react far worse to perturbations than does the true function. And this happens often. Loaded elastic structures, crash tests, least squares. It used to happen to eigenvalue problems until we got better algorithms. So there is a remedy. Use higher precision. Don't use Solon or ordinary interval arithmetic. You've got to do something else. Next page, please. A third failure mode is called the wrapping effect. Now, we're told the word wrapping effect doesn't appear in the book. And it's suggested that no, it doesn't happen because there's no exponential growth in the error. And Zorn arithmetic, same thing on the same page. Uncertainty grows linearly in general. It ain't true. If you have a long computation, especially if you have loops, you run the risk of getting exponential growth. And here is a simplified example. All I want you to do is multiply a vector by a matrix. This matrix is a 20 by 20 matrix. You can get it from MATLAB. It's the Hadamard matrix. Every element is 1 over the square root of 20. But the square of the matrix is the identity matrix. So when you compute x1, x2, it's in an order. Compute them in turn. What you find is you've got a big dimension. The computation is of fair length. But x2n is x0. There'd be no growth. But in any interval arithmetic scheme that we have nowadays, the computed x2n would be too big by this factor. 20 to the power n minus a half. And n is supposed to be pretty big. Well, let's see. What should we do to cut that down? Well, what we do is we say, let's suppose I'll tolerate an error bound that's 400 times bigger than it ought to be. So I'm going to break up the original data into little bits. This is how many little bits you'd have to have, and that's how big they'd have to be. But when you compute this number, this exceeds the number of parallel processors that anybody has, including the Chinese. So it isn't going to work. Mindless, large-scale parallel computing. That's the theme of the book. It doesn't always work. And that's the problem. It doesn't always work. Next page, please. In general, the interval arithmetic community and John figure that if your answer is never wrong, it must be always right. But that isn't quite true, because you can get intervals that are extremely big, much too big. Now, how bad is that? Is that really a bad thing? No, not if you know that the intervals are too big, because if you know they're too big, you'll disregard them or perhaps not compute them at all. But if you don't know they're too big, then you've got a problem. Should you discard a worthwhile project because it appears that it just doesn't work? Intervals are just enormous, so you aren't going to do it. Or maybe what you want to do is some extra work. You're going to undertake extra work only because the intervals are too big and you believe them. This is the harm that's done by oversized intervals. Without an error analysis or another way of doing the computation, there isn't a way to diagnose these kinds of failures. And then, just to make matters worse, the proposal for Zorn arithmetic lacks something called algebraic integrity, which undermines a programmer's faith that arithmetic is at least an approximation to algebra. Let's see what happens. Algebraic integrity is something that the IEEE standard has. If there's no rounding errors, and if you have several different expressions for the same function, they may produce different values without rounding error. But if they do, you can get at most 2 different values, no matter how many expressions you've got. You'll have plus or minus infinity, that's a possibility, or else you may have at least one nan, and you can detect that. You can detect it because nans are obvious, or you can detect it because an invalid operation flag has been raised. But Zorn doesn't have that. You see, it says no rounding errors, no exceptions, and those are the pages in which you'll find those boasts. So different Zorn expressions for a rational function can produce different Zorns. And here it is. U and V happen to be the same rational function. X, Y, Z, they're the same rational function. as functions in the field of rational functions. But sort arithmetic gets 3 different values. And there's no rounding error, and there's no indication that there's anything wrong with these guys. Let's see why that happens. You see, it happens because sort arithmetic doesn't produce an and for these exceptional cases. It produces the whole real number set, extended real number set, including infinity. And of course, if you square that, what you get is all the non-negative numbers, including infinity. And now, once you've got an interval that isn't everywhere, you can squish it in any number of ways, and that's what happens for these examples. But, of course, you could ask, why different expressions of the same function? Well, it's because, as numerical analysts, we know that there are occasions when one formula doesn't work very well. It'll work in this domain, but not in that domain. And so we develop different formulas for different subdomains. And if need be, if a formula malfunctions, as long as you can detect it, you can decide, okay, I guess I should have used the other formula, which may cost more. That's why I used the first one first. If an arithmetic system hides malfunctions, you're going to get into trouble. And it's going to happen to so in arithmetic. Let's see how that happens. Well, it has something to do with what are called C-solutions. That's John's name for an important application of parallel interval arithmetic. You see, what we'd like to find are all the solutions of an equation within a given region. I call these boxes coffins. It can be called a Q box, or it's just a vector of intervals, but it looks like a coffin. And so given an interval program that has very moderate requirements, you have to be able to write a program that majorizes the true equation, and ideally the interval version should tend to 0 as the width of the interval tends to 0, except for rounding errors. Ultimately, there's a limit to how small you can make it. Well, here's the procedure. And this is a procedure for interval arithmetic, usable by Sorns and usable by Unums. If, when you compute this expression at a coffin, if you know that it excludes 0, then you know the coffin can't contain solutions. So you throw that particular interval away. So you partition the one you start with into small coffins. You discard all the ones that can't contain a solution. And then you partition all the remaining ones into smaller coffins and do it again. Just throw away the ones that can't contain a solution and you repeat it until it isn't worth further subdivision. And this is, the book calls these C-solutions. Here's an example. I'd like to find the solutions of this equation. I'll start my search on the interval that goes from 0 to 4. Well, that's a bad choice, because when you compute this, you get an and. Or in Sorn arithmetic, you get everything. So, despite that, we mustn't discard this interval. Instead, you subdivide it. So you can't say that it excludes 0. So you've got to subdivide it. And when you do that, finally, if the intervals get small enough, you'll find some that exclude 0, you'll throw them away, and you'll converge to these 3 values of z. Ah, but 2 and 3 are the only solutions. Z equals 1 is not a solution of this equation. In Unum's intervals, you would get an and. That would tip you off to the fact there's something wrong. In Sorn's, you get everything. There's nothing wrong with everything. You wouldn't know that there's something wrong. So that says C-solutions can include singularities of an equation unless you filter them out. Could we go to the next page, please? Well, the trouble is that if Sorns are never exceptional, it's going to be difficult to know whether you should filter something out. Here's a better example. It uses that function R. And it's 2 equations and 2 unknowns. And it turns out that whenever 0 belongs to a box, it'll be a rectangle, so does 0 in Sorn arithmetic. And 0 belongs to a box whenever one corner is a lot closer to 0 than the others. So it turns out the C-solution process will converge to tiny rectangles clustered around 0. Plus, in Sorn arithmetic, you get one that encloses 0. But it's not a solution. And you can see it's not a solution by looking at the fact that, oh, R can't be any bigger than 1, and I want it to be 9/8. Can't do that. There are no solutions to the equation. C solutions can solve equations that don't have a solution. And there are other ways for this to happen. So, what should we have done here instead? Well, at this point, if the Unum interval arithmetic had replaced Zorn's, doesn't matter if it's units or intervals, and if we used S instead of R, we would have gotten narrow intervals, and then we would have gotten the C solution process to converge to no interval at all. But you choose the wrong formula, too bad. Okay, let's go on to the next problem. Now look, he says he doesn't discourage calculus. Well, look, here's what he's saying. They should work when used in a naive way, the way floats are usually used. Well, that's true. Floats are usually used by ignorant people. You won't know any better. After all, you can get a PhD in computer science without ever taking a course in numerical analysis. At least you can in this country. And here's the essence of the U-Box approach. Mindless brute force application. Do you think that mindless brute force application will compensate for ignorance? I don't think so. Calculus considered evil, discrete. Hey, look, that's the title of the chapter. And then he says, calculus deals with infinitesimal quantities, computers don't. They don't calculate with infinitesimal. It's not true. Calculus does not deal with infinitesimal quantities, it deals with limits. And the infinitesimal quantities are just a shorthand for describing what happens with limits. Bishop Berkeley in the 17th century had the same problem. He used to worry about the ghosts of vanished quantities. But calculus is about limits, not infinitesimals. If you write it with infinitesimals, you're writing a shorthand for certain kinds of limits. We can go into it later if you want. And then here, when physicists analyze pendulums, they prefer to talk about small oscillations. Which physicists prefer to talk about small oscillations? They do that in order to get a limiting case to show you what happens with limiting oscillations of small amplitude. We can even estimate the error in the period if you want to use bigger amplitude. That's why grandfather clocks have such long pendulums, because that way the period of the pendulum doesn't vary much, and that's the whole point of a grandfather clock. What about this? Every physical effect. Now this is his bold face, but he uses the word sampling where I'd use discretization error. This is straight out of his book on that page. Well, he doesn't do that. He doesn't solve physical problems with a discrete model. He says he does, but he doesn't. If you want, we can discuss why he doesn't. So here's what he really does. He treats time as a function of location. But that works only if you know what is conserved, and there are enough things conserved. But how do you know that energy and momentum are conserved? Well, the total energy, kinetic and potential, didn't exist as concepts before the calculus. And, well, it's just an unreasonable way of thinking of the time dependency of physical simulations. He's saying, instead of saying the physical properties depend on time, what he's going to do is say, we're going to treat the time as a function of location. That means you have to know where the system is going to go. But we don't always know where the system is going to go. Even the three-body problem, we don't know where it's going to go. So you can't do that. And in any event, you can't cope with drag or friction. Because with drag or friction, you can't predict in advance where the mechanical system is going to go. Next page, please. Okay, let's...
5 minutes.
Well, I hope I'll finish in 5 minutes. So the book says, here, we offer an arbitrarily precise solution method. Okay. No calculus, just elementary algebra. Well, that's wrong. Here's a counterexample. You see, here's a differential equation. It looks really easy, doesn't it? I mean, there's no higher mathematics here, but the quantity that's conserved is transcendental. You can't get from here to there without the calculus. And if you don't get there, then you have a more complicated calculation than you'd like. Well, you can look at the notes and you'll see how that works out. Now, you have to evaluate an integral. Once you've got these conserved quantities, what you do is you reduce the solution of the differential equation to evaluation of an integral, sometimes in closed form, as for the Keplerian orbits. You can do it in closed form. But for the swing, you have to actually evaluate an integral. So let's see what he says about that. He says, Here is an error estimate. It's an error bound, actually, and it's for the midpoint rule, but he doesn't tell us that. And this is a literal quote from his book. What the hell is that? It turns out you don't have to know calculus to differentiate, because there are programs that will do it for you. If you write a program to compute a function, you can submit it to another program that will differentiate yours and produce a new program that interleaves the computation of your function and its first, and if you want it, second derivative. So you don't have to know how to differentiate, you just have to know that you need one. And you don't have to find the maximum value of the second derivative in order to get an error bound. Next page, please. You see, there are algorithms. Now the book's algorithm, the work is of order 1 over r squared for reasonable functions. He says that I applied it in a case when, the second derivative was infinite. And I mentioned that because the second derivative was infinite, it said instead of getting work to go down like 1 over the square root of r, it goes down a little bit slower because the second derivative is unbounded. But that doesn't matter, it's still faster than this by order of magnitude. And in any event, the fastest algorithms, they go this way. And this is faster by many orders of magnitude than the other stuff. But these schemes give you interval bounds, and that one doesn't. You have to know something about asymptotics. You'll have to follow estimates in order to see asymptotically how the error is diminishing in order to get an error estimate. But you get it so much sooner. And so you now have a trade-off. Would you like an answer real soon, or would you like it a lot later, but absolutely guaranteed? Well, sometimes you prefer one to the other, and in any event, it's not time to overthrow century numerical analysis, not yet, and it's all irrelevant. All this stuff about you don't like calculus, and you should use this numerical method or that has nothing to do with comparing unum computing with what you should compare it with, which is interval arithmetic, but interval arithmetic with precision variable at runtime, and supported by an appropriate programming language. That is the fair comparison. Let's go to that. What does unum computing cost? It's too much, because the widths can vary almost arbitrarily. They're intended to be packed together tightly. So let's see what happens. Well, the arithmetic is going to have larger latency because the unpacking will require more pipeline stages. Oh, it's not just that you have more transistors, it's the wires. When you have a lot more transistors and you have complicated stuff, you're going to have delay on wires. That's what's killing. Memory management. The book overlooks the cost. It says, does the programmer have to manage it? No, the computer can do it, yeah, for a price. The price comes when you want to write unums. Fetching unums is not too bad. I don't think you're going to want to skip through the unums as a linked list. You would probably prepare a table of addresses in advance to go with any set of unums that you're going to read, if all you're ever going to do is read them. That would speed up the process, and it would be tolerable. But if you're going to write unums that can change their width, oh, that's a much more difficult problem, because you can't put the wider unum back where you got it. So that means you've got to use a heap. And if you use a heap, then you're going to have memory defragmentation and garbage collection problems. Oh, come on. You just ignored the cost of those things. And in any event, the cost depends crucially upon how your programming language manages diverse widths. Next page, please.
So you've run out of your 30 minutes, so you need some...
Well, just one more minute. I think you're almost in the last page. What the Sorn arithmetic cost, it turns out that Sorn arithmetic could work if you have sufficiently low precision. And it wouldn't be an unreasonable thing. You wouldn't do it in the fastest possible way, but you do it in the slower way. Next page. How much precision is enough? You see that rule of thumb? Well, that rule of thumb has worked for a very long time. And of course, it doesn't always work. But it works so often that what you have to ask yourself is this. Would you like a result soon, or would you like to wait for it and be absolutely sure? For many results, it isn't worth being absolutely sure because it'll cost too much. I mean, after all, for computer games, who cares? Suppose you have a transient rounding error problem, and it could be a computer game. It'll be gone in a moment. The only sure way is to do it is error analysis. And what can be done instead? Well, we'll have to discuss that later. There is something to do. But here's the important thing. There's some things I don't want to know. And what I don't want to know, I don't want to pay much for. Here's what I do want to know, but it turns out that this thing, uncertainty quantification, this is what is not handled well by interval, SORN, or unit arithmetic. It's a bleeding sore. And then there's debugging. Oh well, we spend at least 3 to 4 times as long debugging as we spend writing our engineering and scientific software. And so that should weigh on our minds. But debugging unit arithmetic and SORN arithmetic, that is going to be a real headache. Okay, I think I can quit now.
May I respond right away to that last
Let
one?
us thank both teams.
All right. So regarding debugging, if you add information to a number, does that make it harder to debug or easier? Because all I've done is taken floating points and I've augmented them with 3 fields that are self-descriptive to assist in finding out what went wrong with the calculation. I'm surprised by this attack. I think you should join me in actually supporting this kind of addition of information to a number that will actually make it easier for people to find out what's wrong with the calculation.
They may find out that it's wrong, but that doesn't tell them that they find out what's wrong.
May I help you?
Well, here, I just, it's
Just
got a
point
tiny
it.
little switch.
Point it at you.
Okay, I think it's working now.
Yeah, it's already done.
Yeah. Yeah, it's one thing to know that something is wrong. It's another thing to figure out why it's wrong.
So does it hurt or help to have extra fields that tell you all about what's going on with the uncertainty bit and where it happened and how big it is and which bit was affected? Does that make it harder to actually use numerical methods and numerical analysis?
Well, what I want to know is where this happened in my
Yes.
program.
So if you have a signaling NAND, it will stop the system and will go to the operating system where there is the call stack. You can find out exactly what routine called it and what instruction, what line of the code. In fact, you can bring up the source code. This is where this happened. So instead of trying to encode numbers, hash pointers to where things went wrong in the 5 quintillion different kinds of NAND that is supported in 64-bit flows, all you have to do is stop and let the operating system tell, this is where your problem is. So I believe all you need is a quiet NAND that says keep on going, or a noisy NAND, a signaling NAND, will stop it and give you all the debugging information you need. The wish that somehow people are going to start using all these many, many different kinds of NAND to encode debug information never happened. People don't use it. It doesn't exist. We've waited 30 years for this to happen and it hasn't happened. I don't think it's going to happen.
Well, it has happened on some of my old computers. Now, you're right, it doesn't happen in modern computers because Microsoft won't give me the source code for the operating system, so I can't fiddle with it. However, what you're saying about debugging would work if you're debugging your own code and it's simple enough. But when you're debugging the code, there's a composite. It's got your stuff in it and it's got other people's stuff in it. You can't just stop, because if you just stop, it'll be too late. You won't know what's going on. You'll stop in the middle of somebody else's program, and you don't know where it is. You don't have the source code, and if you did, you wouldn't want to read it.
So what is your constructive solution to this?
Well, the solution is to know, first of all, whose code caused the problem, and secondly, what kind of problem was it? And if the debugger cooperates, you can even tell the guy where it happened when you ask him to fix it.
Sounds great. I do want to comment on several other things. From the very first page that you presented, where you say a unit is either an exact number or within 1/2 whole, I knew I was going to hear another half hour of complete misunderstandings of every definition in the book. That is not what an inexact unum is. An inexact unum is the open set between 2 exact units, where those look exactly like floating point numbers. I can now mark and fill in all the open spaces in the real number line. There's nothing like a plus or minus half rounding that you get. But the habit of thinking in those terms is lending to, let's bend this to something I can attack and critique, even though that's not what I said. A U-box is the same as a coffin. A coffin is a classic Kahan dysphonism. Let's find the most negative word we can use to describe something. if you have interval arithmetic, you do get these great big boxes that get bigger and bigger, that, go from like 5 to 10, and then suddenly they just blow up. Pretty soon you're minus infinity to infinity. U boxes are one ope on a side, or are exact in whatever number of dimensions they are. They are not like from 3 to 4 or whatever, and they split up into smaller boxes. So it's like confusing a box of Legos with the Legos themselves. You can build a lot of things out of Legos. You can build all kinds of shapes. It's not just a box. And just the definitions that you saw here of what, it's always just a slight misstatement of what I said. Let's warp it over here and then make it say something that wasn't said. It wasn't said that I can solve all ordinary differential equations. I said, here's one that you can solve in some interesting approach. It works for this one. Of course, there's tons of things I can't solve that way. There's lots of problems I can't solve. And I even mentioned some in the book. I did not exaggerate the universality of these approaches the way you're doing it here. Only said it works for this, and it works for this, it works for this. Think about maybe other ways you could make these methods work.
Well, the only thing I can do is quote from the book as accurately as I can, and I think I have. I think I've represented your ideas fairly. I know that you're protesting because now you see the consequences of your ideas. You were trying to persuade people that they can do computations, some of them very complicated, without having to understand what's going on inside the machine, what's going on mathematically. And I claim that that is a false promise.
For all things, yes. It won't work on everything. Of course it won't.
That's right. Well, and then if you don't know when it will work and when it won't.
Well,
Now,
here's the problem, as you have said many times. We have ever more ambitious calculations that we are attempting with ever less numerical expertise. We have 1 million times more computing power now than we had when the IEEE standard was formed. What can we do to improve this situation and make computers a little bit more robust and less error prone and more self-managing when it comes to numerical calculations? I think we have now the ability to do things with all those transistors that can actually save bandwidth, which is another thing I want to correct you on. It's a subtle thing. You talk about memory management being very expensive. It's the wires. The management is not expensive. Management is inside the CPU. That's cheap. It's actually moving the data that costs you. It is trying to reduce the number of bits. The reason I invented unums was to reduce the number of bits going back and forth between the DRAM and the CPU to the absolute minimum, because otherwise we're not going to get to exascale. It will absolutely blow our power budget. We just heard from the Stanford professor, actually in the question and answer section, I said, what about DRAM? He said, oh, that's 60 to 70% of all the energy. So if you can cut that in half, now you're getting somewhere.
No. You're ignoring the fact that if the units vary in width in the course of the computation, you're going to have to put them onto a heap. And if you have to put them on a heap, it means that when you fetch a unum, you've got to fetch an address also.
Right. So we will go between fixed size storage unums, and occasionally we'll wrap them all up and send them off to disk or send them off to DRAM, but we will do it intelligently as needed. But most of the time they will probably exist in unpacked form.
Well, the example in your book of a fast Fourier transform didn't do that.
The fast Fourier transform actually can be arranged so that you're almost always accessing linear ordered contiguous groups. It is possible to do an in-place Fourier transform that keeps on rearranging the data always to pack it. But that said, I would certainly unpack probably an FFT to make the indexing simple. And it would use less energy and do a better job of bounding the answer with fewer bits.
So that means somebody can't use this thing mindlessly, can he?
Not completely mindlessly, no. I've given you tools with which certain things actually can be managed with less effort to find what's going on. Because, as I say, I'm adding information to a number. I'm not taking it away. So if your objection is that I use the word mindlessly, and of course, you can't completely use a computer mindlessly. We wish. You have to use some amount of thought. But does everybody have to know numerical analysis? Does everybody have to know calculus? Do you know only about 8% of the people in the world know calculus? There have been studies trying to estimate what is the overall numerical literacy in the human race. And if only 8% of the people can do numerical methods on computers, we're in trouble, because there's a lot more than that.
Are 98% of the population going to write numerical programs?
Yes.
Let's hope not.
Yeah, right.
Look, I
Not a lot of
understand.
people using spreadsheets that don't know what they're doing.
I understand the desire to make it easier for people to use computers, to make it possible for them to do more and know less. And there's this little box here, the HP15C, which is an example of that. Okay? Yes, you can evaluate an integral. You can solve an equation. You can do complex variables on this tiny calculator. So I'm all in favor of making things easier, but I'm not in favor of telling people that you don't have to know anything. You have to know something, and it's difficult to say what you have to know, but unless people are willing to learn a little bit about numerical analysis, they're very likely to harm themselves or you. We all are going to depend upon software that we get through the web. And if any idiot can write the software and then send out and say, hey, I'm using Unum, so it should be okay. Well,
It's either okay, or we'll say, look, you just got a big error, and you better figure this out. Whereas with floats, it won't tell you a thing. At least you get the warning with Unums. You know something went wrong.
but there is a way with floats. We saw a discussion of that yesterday when someone described Monte Carlo around it. Now, he's got the right idea, except a wrong implementation. And see, you can simplify the implementation a lot and reduce the price a lot and still get the benefit, which says, with very high probability, you'll discover whether your results are contaminated excessively by random. And when it comes to uncertain data, that's the same sort of thing. If you perturb the data and run a lot of experiments, you can find that out. But with Unum computation, you can conclude, because you say, well, I've put in my data as Unums. Each one is uncertain by a half unit in the last place, because that's as many digits as I put in. And then you're going to learn how uncertain your result is because of the uncertainty in data. Well, that's very optimistic.
So I would like to just briefly interrupt and ask, are there any questions from the audience? Well, we can let the debate go on, but we are, close to 6:30. I just wanted to make sure that.
Well, I have a question for you, Dr. Devil. A lot of people use libraries such as LAPAC that I know you're expert in, or statistical packages like R that may depend on large libraries underneath. What do you think might happen in a world with a different number representation with error encoded in it, running through these large libraries, which you've done a ton of error analysis yourself?
So this is one question that you already partially addressed, and I was going to ask that. But let me ask it. So imagine I want to write a matrix algorithm, and I refer to sub-matrices all the time and pass them into other routines and so forth. If all of the objects are variable size, referring to a submatrix suddenly becomes a complicated kind of thing. Would you say that's something to be unpacked to that level?
Absolutely, you would unpack that. And as long as we're talking about linear algebra, the biggest benefit of the Unum definition, and this is more than the environment, is the support for things like fused dot product. So you don't do any kind of rounding or approximation until you've done a complete dot product. This is the idea from Ulrich Kulisch that he unfortunately patented, which effectively prevented the world from getting to it for however long the patent lasted. And now the patent has expired, so I think it deserves some very serious consideration again, because this is a very, very good way to, at this possibly a slight cost of time, get a much more reliable answer. It will obey associativity, for example, as long as you're doing the calculation exactly in the scratch pad. So the quality of linear algebra could improve vastly simply by using exact dot products throughout the kernels and not making that rounding.
So I just wanted to point out that our philosophy in building LAPAC has always been, if we compute something, we will compute an error bound for it. But the number of people who actually use those error bounds is incredibly tiny compared to the number of people who type A/B.
Yes.
And so that's why so we're not going to give up that philosophy, but it has had not as much impact as we would have liked. And so the question comes up in all the approaches we're talking about here too, is that who will use it, and is it worth the cost?
I think you've used the word unpacking in a glib way, because you can unpack if all you're ever going to do is read. But if you're going to write unums, you have to allow that unums may vary in width. And if that's the case, having unpacked them, and then you've got something wider, where are you going to put it?
You're talking about the management of the heat.
And
If you take something out of the heat and now it's gotten bigger and you can't put it back, that's what you're
you
saying.
can't put it back where it was, that's right.
You
You've got to
understand what
make it
unpacking
huge
is?
address.
An unpacked is at the maximum size. So you allow the maximum size that unit can be, which still might be a very usable number of bits and a very large export range. The extra bits that you get that can be used to mark whether something is a NaN or infinity, such that a single bit test actually makes the capacitor float.
So you've got to make provision for what may be the largest width that will turn up under computation.
When it's on the CPU, it probably will pay to do that.
So let me just continue that one. You want to implement Gaussian elimination, and you want to use blocking, which is the standard optimization.
Is your microphone on?
Can't hear you. Okay, let me try one more time. So let's ask, how would we implement Gaussian elimination, where we want to use the standard optimization to make it run at a decent speed, which is blocking. So it seems like we have to, and so we're going to be writing that matrix all the time, because that's how Gaussian elimination works. So it seems like the algorithm would have to run in sort of standard arithmetic, basically, because you're going to be reading and writing the matrix over and over again. And so you would just be effectively running in standard floating point, maybe with your representation, but the semantics would be the same.
It would be similar. I think that's one way to do it up to a certain point. As soon as the matrix gets so large that you discover you have to store it, say, on disk, then it's worth paying the price to pack and unpack these things. It's always an option. You don't have to do it. But the rate, right now, memory is 200 times slower. It takes 200 times as long to fetch an operand from main DRAM as it does to do a multiply add-on. You can get an awful lot of management type things done in that time and figure out what's going to go where. It's in your gut, it says, oh, that's going to be really expensive. Spec it out. Actually, do the calculation of how long these things take. It's not something you can just, from an armchair, say, oh, that's going to be really expensive. You'd be very surprised with the design rules of 2016 say you should do, and that's expensive versus not expensive. Moving data between DRAM and CPU is a killer. You want to do as little of that as possible. You want every bit to count. That's what I'm trying to accomplish. So anytime you can economize.
I would hope that maybe the future challenge is to write optimized block Gaussian elimination using your arithmetic and see what the overhead might be.
Sure.
Well, there is a second problem. When you minimize communications costs, you end up using algorithms which, in some sense, have to anticipate what is going on. In that case, they may require rather more precision than you thought in order to survive. And I give a citation to that in one of the documents on my webpage, where a graduate student worked it out and found, my goodness, you may have to use double precision or more when actually your data is in floats or smaller. This means it's hard for you to predict how much precision will be needed if you're using an algorithm that economizes very greatly on memory movement. The algorithms that economize on memory movement are sufficiently strange that some of them require extraordinary precision in order to survive.
So I guess we're talking about solving least squares with the normal equations, just to be very concrete, because you want to compute x transpose x and double. So you sort of have to know that ahead of time. And there's a question from the audience.
Yes, I have a question about the cost of performing the operations with UNO. Suppose you have an iterative solver where you multiply matrices, and you have some nice size, let's say 128 by 128. Chances are, every time, if you impose a limit on the number of bits you represent, every time you do an FMA, practically, you will end up rounding. So for UNOs, you're going to have imprecise bit set, right? Okay. Now, for matrix multiplication, I have to do, in this case, 128 FMAs, one after the other. And chances are very high, at every step, I'm going to have an imprecise value. So if I understand correctly, after computing one element of my matrix, I'm going to end up with 128 boxes or so. Maybe
You're
I
talking
completely
about a dot
understood
product?
the representation, but the point I'm making here
Is this the dot product you're talking about? You're doing matrix vector multiply?
you do a matrix multiplication where you take two vectors in order to get one result, right?
There's one
value.
rounding error at the very end, or what you would call a rounding error. It's done as if it was an integer multiplication.
So my real question is, if you have an imprecise result every time you do a plus, how many units of storage do you need to store the result? Is it
My
one?
answer is you do not do an exact after every plus. You group the entire vector. You do a dot product, all in exact arithmetic.
So you're proposing
Then-
implement an arithmetic unit that takes together 128 values,
It's called the exact accumulator. yes.
and that's exact accumulation.
You don't
So if
usually,
I go to 1024
Oh.
matrices,
Yeah.
I should beef up my
okay,
FMA.
look, most of the time, with extremely rare exceptions, you can do the scalar product, accumulating the products with FMAs, if you want, or you can accumulate them in variables that have twice the width of the operands. So you have A times B, say A and B are floats, A times B, you compute that in double and add it into a double sum, and almost always what you'll get will be perfectly satisfactory. And that's one of the reasons why Kulish's scheme, which would evaluate it exactly, isn't very popular. It's because it hardly adds anything to the value, only in extremely special circumstances. So, for your purposes in graphics, I think that's what you have in mind.
No,
Am I
not
right?
really. I mean, we have gems right all over the place.
I can't hear you.
Gem, right, matrix multiplies. So let's
Oh.
say take just the matrix multiplication. And my real question is, how much memory do I need to store my result under random circumstances?
Whatever
If I use onums, I understand what works for floating point and how to deal with error. I'm just curious for onum, how much memory do I need to store my results, or how much price I need to pay for the extra computation?
Are you
And
afraid
I-
that somehow it's going to become a gigantic number? Is that your fear? Because you set the environment. You say, I want a maximum of this many bits of
It's the
exponent.
real problem I'm facing here. I understand the benefits. I do not understand the cost.
And I'm
From
telling
what
you
I've
that,
heard today, it's either going to be an extremely costly arithmetic unit, or it's going to be an extreme cost in terms of storage. If I use onums. I mean, it's my feeling. I didn't read it.
I don't think you understand. It's not unlike saying, I'm going to do this in double precision. You know the result's going to be 64 bits. I'm going to say, this is the biggest exponent I can have, this is the biggest mantissa I can have. That's the size you're going to get to. It's not going to go beyond that without your control. You said that you can try that and see if it works. And if it doesn't
So
work,
let me make it a little simpler. Suppose you have value A and value B, and they are both inexact, right? Which means they are between two values of the intervals,
Right.
right? But whatever the unit in the last place equivalent is to onums. I add them, A plus B. All of a sudden, instead of saying one inexact bit at the end, one ULP at the end, I'm going to have two ULPs.
to
I
what?
cannot, whatever we call
So the
ULPs
width
in onums,
adds the intervals,
right?
which
So
you
I-
have two intervals. The width
So
adds-
I'm adding two numbers that are not exact.
Mhm.
I cannot store the result using only one unum.
Sometimes you can.
I have sometimes, but on the average, no, you cannot. So I will have, for simple addition of
Yes.
two inexact numbers, I have to double my storage.
Yeah.
Well,
Now this is
You
one
really need to read the
step,
book.
and we're talking about the very simple matrix multiplication, which will end up having an n cubed cost in terms of storage
No.
on the average case. That seems a little bit extreme.
It's not the way they work. As I said,
Real, I'd like to understand how.
well, you're getting into something where you just about have to read 2 or 3 chapters of the book to understand. But-
Can you explain in few words why am I wrong?
Well, first of all, if you have, let's say your numbers are where you would store floats, you have replaced them with units. So you have inexact quantities here.
And it's not about replacing the unums, it's about how unums work. I don't think you explained that. You made the
In
claim
general,
about
a
how
unit is
wonderful it
not
would be
closed.
to have a world in which things work magically. But I do not understand the magic. That's my
I think
problem
interval
right now.
arithmetic was designed to help you with your problem. Namely, each of your arguments is uncertain, and if you use not the conventional two real number brackets for intervals, but you use the center and radius scheme for intervals, then you'll find that no matter how wide your operands are, if the uncertainties are small, you will not have to worry about a great deal of storage for the accumulating uncertainty. But you will have to worry about the fact that if your uncertainties are correlated, the correlation will not be taken into account, and so you may end up with a very pessimistic estimate. But otherwise than that, interval arithmetic was designed to cope with your problem, I think, if I understand it. And there isn't a simpler way to deal with it. If you knew in advance that none of your arguments was more uncertain than, say, 1 part in a million, then it would be possible to say something in advance about the inherited uncertainty in the scalar product, but it would be very pessimistic.
So let me just say we've been reminded that dinner is at 7. And so I would like to invite both of our speakers to make some closing remarks. So maybe 1 minute of closing remarks for each one. And then, of course, the debate can continue with dinner if we desire.
As I said, we have much more power than we used to have. Maybe I didn't get it right, not on all counts, but I tried to get people to think about the fact that we need to use vast advances in technology to improve the quality of computer arithmetic. So we have the opportunity to do so. I would very much like to do so with Dr. Kahn's help, not as an adversary. He has been a man I've admired all my life. I've been doing numerical work since I was 15. I've been making use of his calculator since I was probably a freshman in college. I've learned so much from this man. I'm not happy being on the other side of the fence from him because I think we do want to accomplish many of the same things. He may argue with my style a little bit, or a lot, but I think we really do want to see the same thing come out of numerical analysis and computing.
Okay, my position is that we should not try to oversell schemes. We should try to be conservative in what we offer because people will depend on it, and if they depend on things that can fail from time to time, then it's necessary for us to estimate what is the insurance premium that should be paid in case the system fails. So if a system isn't foolproof, what is the probability of failure? How much will the failure cost? You multiply the two together, you add that up over all the possible failure modes, and that gives us an idea of how much an insurance premium should cost. There's the choice. Either the system has to be foolproof, or if you say that it's foolproof but it isn't, then I would like to know what insurance premium will Lloyd's of London charge you. Or you can tell people, if you want the answer in this hurry, you're going to have to take a certain risk. And we're accustomed to that in life. There are some situations where you have to accept certain risks in order to get things done in a reasonable time. In numerical computation, there's a lot of that. And it doesn't mean that we're just guessing. It means that we've tried to strike a balance between getting something in a reasonable length of time and having reasonable confidence. I don't think that the world of computation is quite as uncertain as John says it is, but then, since I'm a numerical analyst, I would see things differently. I do agree, however, that there are people who will write computer programs who are completely innocent of any exposure to the hazards of floating point. I agree that that is going to happen. And unfortunately, it's going to happen no matter what John and I say or do.